That's windowless Emacs. It's an alias.
Oh.
Right.
Oh, okay.
That's my own alias. Yeah. Okay, so it just compiled, and so there you see we have the md_tau. And so now you would just run this just like you run any other code. You want to make sure that, so let's see, md_tau. So you just have your traditional regular old submit script, and make sure that you have the right envapage loaded. And then this MD code takes two arguments. One is the size of the system, and the other is the number of iterations. So we're just going to use those values. At this point, you can also export tau options. So if you wanted the full call path, for example, so you set tau_call path equal to 1. And then set the call path depth. Okay, so this is where you do all your runtime options just right before you run it. And I think that should be ready to go. So we're going to run this over 16 cores in the development queue.
What does tag_affinity do next to IB run?
So that's that is a script that the Ranger folks have developed. So that's a standard system script on Ranger, and I think in general when you run an MPI code on Ranger, it's recommended that you use tag_affinity. It controls the process placement on these multi-core nodes on Ranger. So it makes sure that those are placed nicely, and so I've run codes both ways, and it works both ways. It's just something that's good to have. I think in general, the Ranger folks could comment more thoroughly on that.
Yeah. Do you want me to make a comment? This is Kent.
Sure, Kent.
Yeah, so it's exactly what you said. It places the ADOT out on each of the cores in a specific way, and it also forces a certain type of memory policy that may work much better for you. Since what happens in a previous job is sometimes people do I/O, and it uses the memory that's associated with core 0. And if the people do not remove the files and they just write to them someplace in Lester, then what happens is it stays in memory. And what happens with the default allocation policy for memory, it may spill out to another socket on the system. And so what it does is it forces your memory allocation to be on that socket, and so it makes sure that you get that it gets its specified memory or its proportion of memory that it's needed. And so in most cases, you're running 16 ADOT outs on a node with 16 cores, there's no problem. But sometimes if there was I/O being done extensively before you, it may make a little bit of difference. So lots of times it won't make a difference, but sometimes it does make a difference. So it's good just to stick it in there.
Okay. Yeah.
Okay.
Thanks, Kent.
So do you does that etcsecuritylimits.conf?
I'm sorry, I didn't hear.
You said you limit the memory. Does that change the etcsecuritylimits.conf for the user?
Actually, what your total memory is the thing that's actually looked at. And when you submit a job that has 16 ADOT outs, you get a particular amount of memory per A.out per process. If you submit a job that has less than that, then you get, as say you're only running 8 A.outs on a node, then you'll get more memory per A.out, and that's handled by the SGE. So that's the only place where it's handling your memory. What TAC Affinity does is sets the policy for each of the sockets in terms of the allocation of memory from any of the cores on that socket.
Thanks.
Okay.
Yeah, so there's lots of issues to think about with multi-core machines. So I've just submitted this. I've just submitted this this job to the queue, and it's waiting there. It's in the development queue, so it should go pretty quickly. But in the meantime, I previously submitted a job that ran. So when this job runs, this is what you should get. Okay. So you'll get the normal output from your job, of course, but then Tau will create all these profile files. And so these numbers correspond to the task that each profile was done on. And so we ran on 16 cores, 16 tasks, and so there's 16 files here numbered from 0 to 15. If you run a hybrid job, then you'll have the first number will correspond to the MPI task, and then there will be the second number will be the number of the thread that ran on that MPI task. That's another thing that you can look at if you have a hybrid code you want to look at. So in any case, you get these profile files, and then the thing to do with these is to run paraprof and then a double dash pack, and then you just give it a name of whatever you want. So you just call this, and then you give it and then it should be a .ppk file. So you name it something .ppk and let it run on that. And there you've got this .ppk file. So then this is something that you can copy back to your local machine, and I've already copied this. So I put another directory here on that examples link that I gave you on the Google Groups. There's one for lamps and unres. Here's one for this simple MD code. And so if I click on that, then I can open it in paraprof, or you download it and then run paraprof in the name of the file. And so now we've got this. Now we've got this.
Question.
Yes.
Hi. Could you please tell us where your job script is, and we can give us permission. We can read your file and look at your directory, so that we can copy your stuff and we try what you did.
Okay.
You can just have PWD, for example, give us a reading permission.
Let's see. Yeah, I can do that. So okay. So I think you should have permission to look in this now, and there's the directory if you can get to that. Now this is the process is the same. So if you just have a basic script, I guess the thing I could put the md.cpp file thing that I compiled, that's on the website already, the Google Groups under MD Exercise 3. I could quickly, yeah, actually what I'll do is, this will be a little bit quicker, and there's a link already from the Google Groups to this, is I will send this over to that examples page that you have a link on to from the Google group. Okay, so now if you follow that link on my page on the Google group and go to MD, then you have this md.cpp file and the md_tau.ppk file. And so you would just follow this same process that I'm going through here if you're on a different machine other than Ranger, but with the appropriate submit script and paths to the make files and all that. Okay. Does anyone need anything as far as, does that work for what you need?
Yes, I'm just trying to get your JavaScript so that.
Okay, yeah. So I've got a JavaScript submit_tau.sh, and it's really the only thing that's different about this from a typical script is just I've got these tau environment variables set. But I just sent that over to the page also. Just designates it's for Ranger. So okay, so I showed you we've got this .ppk file, and I opened it from this web page. I downloaded it, or you can SCP it to your machine. And I just got to find it now. I'll just open it again. Okay, so we've got all these different bars here. And so I just wanted to show you a little bit of how to manipulate these things and what you're looking at. If you hover the pointer over it, then it will give you information about what you're looking at. So it's got a standard deviation bar at the top and a mean. So we've got the average across all the cores right here for that particular function. So that's the average time. And that's nice to get an overall view of what's going on. If you click on mean, if you left click on it once, then you'll get the average time across all the functions. So that's what I was showing you initially. And this is nice to get an overall view, but you got to be careful because since it's an average, some of these functions may be taking place only on a certain processor and not on any of the others. And what you get is it just looks like it only runs for a short time, where in reality it might be running for a very long time on one of the processors and just a very short time on the others. So you could have, when you look at the mean, then you of course miss the load imbalance information. So what it's nice to do when you get this view, so see how it's all, they perfectly line up. So this is what I was talking about, that the view is normalized by default. I sort of wish it weren't because it can be sort of deceptive that it appears that everything is finishing exactly at the same time. So what you want to do is go up to the options here and uncheck normalize bars. And it turns out that, well, it actually is load balanced. But sometimes you'll see big differences. Although these functions take quite a bit, the time varies a fair amount in these functions. So the other thing you can do to see this more clearly is to uncheck the stack bars together. And so it breaks these things out. And you can see the individual patterns clearly for each function. And so if I